So we had just started talking about benzene, and I told you that I told you about benzene. We did the structure of benzene last time. I talked about the ring structure. What did that mean? I told you that it was a lot easier to imagine benzene like this, which is known as the Kekule structure, but Cambridge doesn't use this. Cambridge uses this one. So it's kind of Assalamu alaikum. So it's kind of double bonds alternatingly arranged, and eventually the double bonds kind of get mixed up, which is why you get a ring-like structure at the end. This was the close-up view of this thing, that you had a carbon atom which was sp2 hybridized, where it was making 3 single bonds, 3 of them, and the 4th electron was available as a p orbital. This carbon atom also was making 3 bonds, 3 sigma bonds, and the 4th electron of this carbon atom was also available. So what eventually happened was that the 4th electrons, they kind of got mixed up. The p orbitals, they ended up forming a pi electron cloud, and all p orbitals overlap and a delocalized pi electron cloud is formed. So instead of getting 3 double bonds, you get all of them kind of get mixed up. And we also discussed that the electron density is lower compared to pi bonds in alkenes, as the electrons are delocalized over a much bigger area, which was that a p orbital would not only overlap with the carbon atom on the left side. I mean, it's basically trying to make 2 double bonds with 1 electron. I mean, it's got 1 electron over here that's buzzing in this area, in this p orbital. It's trying to overlap with the carbon on the left side. At the same time, it's also trying to overlap with the carbon on the right side. So the electrons are kind of more distributed in this case. Unlike this other thing that we did, this pi bond that's formed in an alkene, the electron density is kind of right in the center. It's not distributed. It's not spread out over a much bigger area. So it's got a larger polarizing power. Alkenes have a much greater polarizing power. So we did discuss this, and we talked about benzene, that the electron density in benzene, it's kind of, I mean, the bond over there, it's not really a double bond. It's like something that's in between a single bond and a double bond. And I showed you the bond energy table as well. So they gave the bond of benzene a different value. It was weaker than a double bond, but stronger than a single bond. So it's got less polarizing power. I can add that. There's going to be a lot less polarizing power. Is that clear? Aruba, is this clear? Minahil, everyone else? Ethan, is this clear?
Yes, sir.
Yeah. So it's going to have less polarizing power. And we started off with the first reactions of benzene. And the first reaction of benzene that we're going to do is going to be known as bromination or chlorination. And that's it. I think that's we didn't do anything else. Yep, we had to study the mechanism of this. So unlike normal alkenes underwent this reaction. Where's the reaction? Just a second. So normal alkenes, when they reacted with bromine, there was no special condition requirement. No catalyst was needed, because this double bond electron density was really high and it would polarize the molecule strongly. So there was going to be strong polarization. What that basically means is that the electrons over here are going to be repelled very, very strongly. This bromine would have a very strong slight negative charge. This bromine over here will have a very strong slight positive charge. And the top bromine will get attracted and the bottom bromine is going to be repelled. It's going to be attracted. The top one is going to be attracted to the double bond, which is why you get a reaction automatically. It's a very fast reaction. No special conditions are required. Now over here, the issue is in this case, and I'm going to pick this benzene. I'm going to show you on this benzene first. So over here, the issue is, and let's talk about the mechanism. And here's my benzene. Let me just simplify this and just show you the pi electron cloud. So just removing everything else. And I'm going to get rid of this as well. So anyway, so I've got this benzene, and there's a bromine molecule that's kind of attracted to it. So let's say there's a bromine molecule that's coming in, which is kind of attracted to it. Or let's say it's initially non-polar. It just randomly comes around and tries to collide with the benzene. So there's this electron cloud over here, and this electron cloud is going to repel the electrons over here. But the problem would be that the polarization is not going to be very strong. It's going to have a slight negative charge. This one will have a slight positive charge. But the only problem is that this positive bromine over here, the one that I'm about to shade, this positive bromine over here, it's not as positive as we would like it to be. I mean, it's not positive enough to attract the electrons from the pi electron cloud. I mean, the force of attraction is not that strong. The polarization is not that strong. So there's going to be weak polarization. And why was there weak polarization? Because the electron that was supposed to be over here is distributed not only with the carbons on the right, on the top, but the electron is also distributed with the carbons at the bottom. So the electron density at any particular point in the benzene electron cloud is kind of low. Other polarization is, I mean, it's this thing that that these electrons are getting pushed away because of electrons over here. Electrons repel other electrons. So the electrons that are in this double bond are going to be repelled by the electrons that are present in this electron cloud. Adam, is this clear? So what would happen is that if the electrons get pushed to this side, towards the right, this would become more negative and this one would become more positive because the electrons are at the moment closer to this bromine. I mean, I can show you what's basically going on is that these two electrons would be kind of pushed away or closer to one of the bromines and away from the other ones. So, but the whole problem is that the polarization is not that strong. It's a weak polarization. And I'm going to write down the reason for that. The reason for that is that benzene's pi electron cloud has low electron density. So it's got a low electron density, which is why that's the reason why there's less polarization. And the bromine is not that positive. So it's not going to be attracting these electrons very strongly. So is this point clear? The first thing, everyone, is this clear?
Yes, sir.
Yes, sir.
Lubena, clear? Shafak, is this clear?
Yes, sir.
Yes, sir.
I said now the whole problem is that the reaction will not start until you add a catalyst, because you need to make this more positive, you need to make this more negative. You want this to be more positive so that it attracts the electrons in this electron cloud. So what you need to do is you need to kind of push the electrons further away. So you're going to add a catalyst. A catalyst is added in the form of FeBr3, or it could be AlBr3. We wrote down the condition, so you could use both of them. Now, Fe is iron, or all transition metals. The thing that's wrong with transition metals is that unlike normal metals, they don't really like to lose electrons. They actually have this very weak attraction for electrons. Like transition metals, they don't like to lose electrons. Like look at gold or platinum or silver. They don't like to lose electrons. They don't like to form ions. And the reason they don't like to lose electrons or form ions is that they have a strong attraction for electrons. So iron would kind of pull the electrons from the other side. So this is what's going to happen. That adding the catalyst, this benzene electron cloud over here is trying to push the electron to this side, and iron on the other side is trying to pull the electron. That would kind of indicate, increase the polarization. This bromine will now be more polarized because of the iron over there. It's going to become more negative, and this one would become more positive. And eventually this bond is going to break. The positive bromine will eventually now get attracted to the electrons over here, and the negative bromine will get attracted to the iron on this side. So instead of just there being a push, there's a pull from the other side now, which is trying to pull the electron from the other side. So is this point clear?
Yes, sir.
So I'm going to add this, that Fe catalyst, FeBr3, from the other side attracts bonded electrons in bromine molecule. And that's the reason which kind of increases polarization. Okay, so your molecule gets more polarized. In the case of alkenes, you didn't have that issue. In the case of alkenes, the electron density was very high, so all the push came from the alkene, and the bond would break. The electrons would get pushed away. But over here, that's not happening. The electron density is low. So that's the first step. That's the first step of the reaction, and the next step that's going to happen is this negative bromine will get attracted to the Fe. The positive bromine will get attracted to the to this thing, to this entire benzene structure. So let's talk about this. Let's redraw this. So here's my benzene, and on the other side, I've got my FeBr3. The bromine molecule has been polarized. You got a bromine +1, and you got a Br, which is -1. Okay, so the bond has been broken. The Br +1 is now going to be attracted to the electrons in the pi-electron cloud. It needs one electron. So it sees the electron cloud over here. It specifically sees this electron over here. There's an electron in this p orbital. I mean, at the moment, it's spread over here on the, it's overlapping with the atom on the top and with the atom at the bottom. But the Br +1 is going to pull that electron away. So basically what would happen is that this p orbital over here would stop overlapping with the other carbon atoms. And the p orbital electron is going to be pulled towards this bromine. And the bromine positive charge is going to go away. It's going to go away, obviously, because it got an electron from this carbon atom. So is this clear?
Yes, sir.
Okay, everyone else, is this clear?
Yes,
Okay.
Yes.
So that is what has happened. The bromine positive broke away. It got attracted to the electron over here in this carbon atom. The electron was initially overlapping with the carbon on the top and the bottom, but the electron got pulled towards this bromine, which is positive. So now where did the positive charge go? The positive charge is gone on this bromine atom, but the positive charge is going to appear on the entire benzene ring. There's going to be this positive charge, and the reason there's going to be this positive charge on this benzene ring is because the benzene ring is now electron deficient. I mean, it lost an electron. I mean, you had a benzene ring with 6 electrons, 6 p orbitals all overlapping, but then one of them left. One of them got attracted to the bromine, so one of them is gone. So that means the benzene kind of lost an electron. So this is now electron deficient. Is this also clear?
Yes, sir.
So, and the final part is that I mean, what happened to this other Br minus 1? It's going to be attracted to the FeBr3 catalyst. It's got these 2 electrons. It's going to go over there, and it will eventually form a dative bond with this one. So let's try and make a dative bond. So this Br with its lone pairs will eventually form a dative bond with this Fe. And the entire thing will have a negative charge because a neutral molecule ended up bonding with a negative ion. So neutral plus negative, that is overall it's going to be negative. So the FeBr3 turns into this thing. Is this also clear?
Yes, sir.
Yes.
So now, Ethan, Mohammed, is this clear? Shafaq, clear?
Yes.
So,
Yes, sir.
so now the last step. The last step is the benzene needs its electron back. It needs its electron back. So what it would do is it sees the electrons of this H atom. And what it would do is it's going to try and pull those electrons away from it. It's going to try and pull those electrons away from it. And the p orbital would be reformed and the benzene pi electron cloud would be back. Okay, that's what's going to happen. So the next step is this is because the benzene is now electron deficient, and so it's electron deficient. It pulls those electrons, the H leaves. I mean, the H is lost. Okay, the H is now a positive ion. Okay, it's got a positive charge now. Okay, it's going to leave. It's going to leave its electron over there. So the electrons are going to come back, and we can just copy paste the p orbital. So the carbon gets its pair electrons back. This bond over here is going to go. Okay, the electron is back because H left its electron back. And finally, the last thing is that the overlapping would again start happening. They would start to overlap again above and below. And the overlapping would be back. But what has happened is that the H has now been substituted with the bromine. That's why this is substitution. The H, let me just. I say in the whole process, the Br has come in and the H is gone now. Okay, so is the whole process clear? This is what has happened. The positive bromine came along. The polarization happened because of the FeBr3. The positive bromine took the electron from the carbon atom, which was overlapping with all the other carbon atoms. The overlapping ended at this carbon atom because bromine took its electron. So bromine would come and bond with it. And then the H would give up its electron because this benzene ring would be electron deficient. So it would pull the electron back from the H, and the H would leave, leaving behind bromine. So there's a substitution that's happening. The H has gone and the bromine has taken its place. So is this point clear? Whole thing, what's happening?
Yeah.
Right. And the last part is what happens to the H. What happens to the H is that where did the Br minus 1 go? Br minus 1 went and attached to this one. So the Br minus 1 is going to come back. It's going to be attracted to the positive H, and together they're going to form HBr. So together they're going to end up forming an HBr molecule. So an HBr molecule is formed. And all of this, the catalyst is reformed because the Br minus 1 came along, joined it, but the H plus 1 is going to pull it back and HBr molecule is going to be formed. So the catalyst remains unchanged. So catalyst is recovered. So you got these three steps. Step number 1 and step number 2. This is so all these three steps, TK, that's it. But obviously in the exam you can't really draw. I just wanted to show you a detailed version of this. So I'm going to draw the mechanism that you're supposed to draw. TK, I'm going to draw that mechanism, and that mechanism would be kind of the same. So just remember, this is what you're going to draw in the exam. That was just a very detailed picture, TK. And so the exam mechanism is you had a benzene, and let me just draw one benzene, just 1 second. TK, so just 1 second, let me just draw one perfect benzene so I can use it for later. So I think that should do the job. That's your benzene ring in the middle. Still not good enough. Just 1 second. So let's go with this. And that's your benzene. This is the mechanism that you're going to draw in your exam. A bromine molecule approaches it. So you got a bromine molecule coming in. You got an FeBr3 catalyst. That's the first step of the mechanism. Draw the curly arrows. The electrons from the benzene are going to be, I mean, the first thing is polarization would happen. This would become partial positive. This would become partial negative. Draw the electrons. The electrons are going to be attracted to Fe. And at the same time, the electrons from benzene would be attracted to the positive bromine. So this is what's happening in the first step. You've got benzene that's pushing the electrons over here, and the electrons are getting attracted by Fe on the other side. That's the first step. This is what you're going to draw in the paper. Then the next step, okay, which is kind of the same as what we did earlier. Then you've got the next step. Okay, and the next step is so the next, just a second. So now the next step is the Br minus 1 second. Br minus 1 goes, takes its lone pairs with it, and natively bonds with it. It's not going to be just 2 dots. And the whole thing gets a -1 charge. And this Br positive comes along, bonds with one of the carbon atoms. Which already had an H atom. And the benzene ring disappears because it's now electron deficient. So it's just going to be partial now. It's just going to be on 3 carbon atoms. Just a second. So it's going to be partial now. It's going to have a positive charge. Okay, that's what you're going to draw. And in the next step, you're going to show the H atom. Okay, so in the next step, what you're going to do is you're going to show the H atom, losing the electrons, giving it back to benzene. And that's going to be your final step. So let's do that one over here. So the benzene electron cloud would be reformed. The H would leave. So the H is gone, giving its electrons back, and the benzene electron cloud would be reformed, would be complete again. So it's going to be complete again, and you've got a Br sticking there in the place of H. You had an H over there, but now you've got a Br that's attached to this carbon atom. You're going to have an HBr molecule because this Br minus 1 would be gone as well. And you'll have an HBr molecule. So exactly the way we did it earlier, except that now I've drawn the exam version. This is what's supposed to be there in your exam, or how you're going to draw this. So that's the second one. And then after that, you've got this third step. So step one, and so that's step one, and then you've got step number two. Okay. So is this clear? The whole mechanism.
Yes, sir.
TK, and remember, this is very important. This is something that comes, I mean, you don't have a lot of mechanisms in A2. So that's the one that comes the most frequently. TK, remember all of this, what happened over here. They might ask you, why do you need a catalyst? Why do you not need a catalyst in alkenes? The main difference is the electron density in the pi electron cloud, much lower in this case. So that's your entire mechanism, and electrophilic substitution happens. The same as with chlorine. Chlorination is exactly the same. So that's about mechanism, and we can now talk about the second electrophilic substitution reaction, and that is nitration of benzene. So the second one. So reaction number two, again, electrophilic substitution, which is going to be exactly the same, identical, except that it's a completely different reaction, but the whole mechanism is exactly the same. So this one is nitration of benzene. Okay, so you've got nitration. Just hold on a second. So now the reaction in this case, I just need to draw the benzene structure. Let me just bring it up. 1 second, this one. Okay, I think I have another benzene. Just 1 second. So here's my benzene. And I'm going to do nitration. Nitration is simple that what happens in nitration is that you use concentrated nitric acid and you use concentrated sulfuric acid. Okay, so it's a completely separate reaction from the previous one. And you use a temperature of 55 degrees centigrade, somewhere between 50 and 60. And what happens is that just like substitution, what happens is that you get an NO2 group that substitutes one of the carbon atoms. Sorry, hydrogen atoms. So you get an NO2 group that substitutes one of the hydrogen atoms. So that's the condition, that's the reaction. So you've got bromination, chlorination, and you've got nitration. The reaction has 2 steps. So step number 1. Step number 1 is the production of an electrophile. That's your step number 1. How is an electrophile produced? So what happens is that, and you have to remember this equation, that 2 H2SO4 molecules, they react with the nitric acid molecule. And there's water present. And they react together to form 2 HSO4 -1 ions, and then a 2+1 nucleophile is produced, plus H3O+1 is produced. I'm not sure if water is necessary in this case. Just balance 4 + 1, that's 5. So you've got 2 + 3. So I don't think there's water necessary in this equation. The equation kind of looks balanced. Just check if the equation is balanced. 8 oxygens, and you've got 2 over here and 1 over here, so that's fine. The equation is balanced. Okay, so you have this first reaction. That is the production of the electrophile. So concentrated nitric acid and concentrated sulfuric acid are specifically used so that the NO2+1 nucleophile electrophile, is produced. Okay, that's the first step of the reaction. And we're going to talk about the other steps. The other steps are kind of the same. Okay, what I'll do is, once the NO2+ electrophile is produced, I'll just copy this one. Okay, once that is produced, kind of the same thing happens. So if I just copy this, instead of bromine, you're going to have NO2+1 over here. So remember, there is no catalyst. There's no such thing as a catalyst in this case. So, I mean, FeBr3 is gone. I'm just going to substitute this with NO2+1. That's the first step. The NO2+1 needs electrons, so it's going to be attracted to the benzene electron cloud. Forget this, remove all of this. And then what happens? The NO2+ goes and bonds just like, and it has to be, it's fine. So the NO2 goes and bonds with the benzene. It attracts electron. The electron cloud over here becomes electron deficient. It becomes positively charged. In the next step, it attracts electrons from the H atom. Where does the H go? There's an HSO4 -1 ion, and that's going to be attracted to the H. So the H positive is going to leave its electrons there, and the H+1 would join with the HSO4 to form the H2SO4 molecule back again. So the rest is kind of simple. It's you've got NO2, and the H2SO4 is reformed. So what you can say is that the H2SO4 molecule kind of acts as a catalyst. It helps in the production. It helps in the production of the NO2 plus electrophile first. That electrophile is produced. That electrophile goes and bonds with the benzene carbon atom and takes away electrons from it. So the electron cloud becomes electron deficient, just like what's going on over here. In that case, you had a bromine positive that was bonding to it, and the electron cloud disappeared from this side because the bromine took its electrons. Now you've got an NO2 electrophile that's doing that. And in the next step, the H loses its electrons, leaving the NO2 behind. So the same thing exactly is happening in this case as well. So the exact same thing happens over here. So two mechanisms that need to be remembered. One is both of them are electrophilic substitutions. Both of them are the same mechanism, except they're different reactants. One is with bromine or chlorine, and the other one is with nitration of benzene. So is this all clear?
Yes, sir.
Yes, sir.
Okay. So remember, these are the two main mechanisms of benzene: electrophilic substitution, nitration, and chlorination. So let's continue with this in the next class then. Everyone, take care.
Thank you.
Hafiz.